Hello dear students. In the previous session we were discussing the theorem let n be an arbitrary normed linear space, then for each vector x belongs to n, the scalar valued function fx defined by fx of f is equal to f of x for all f belongs to n star is linear and continuous. Then there is an isometric isomorphism between n and n double star, that is nothing but your second conjugate space of n, by phi from n to n double star phi of x is equal to fx for all x belongs to n. We were discussing this theorem, right? So in the statement they have given that n is an some arbitrary normed linear space and they have considered one arbitrary vector, say x, and that belongs to your normed linear space n. We have to prove that there exists a one more thing they have given is fx is a scalar valued function, and you can define this scalar valued function by fx of f is equal to f of x for all your f belongs to n star. N star is nothing but conjugate space of n, right? So these are all the given thing. We have to prove that this fx is linear and continuous. This is first part of your proof. In the second part they have given that there is an isometric isomorphism, that is phi from the mapping they have given is phi from n double star. This double star is nothing but second conjugate space of n and defined by phi of x is equal to fx for all x belongs to n. We have to prove that this mapping is an isometric isomorphism. So from the definition of isometric isomorphism, we know that if I want to say this mapping is isometric isomorphism, then we have to prove that it is a linear map and it holds one condition. Along with this we have to prove that norm tx is equal to norm x. Since the mapping is phi, we have to prove that norm phi x is equal to norm x. So this is what we are supposed to prove in this theorem. In the previous session we have already proved that our f of x is linear as well as continuous. Now let's move to the second part of the proof. Okay. So the mapping is phi from n to n double star. I can rewrite this as n star whole star or n star, all are same. Okay. So first I will consider two vectors in n, that is normed linear space n. I want to prove phi is 1 1. For that what I will do, I will consider phi of x is equal to phi of y. From this I will prove that x is equal to y. Okay. So phi of x is equal to phi of y means from the defined thing I can write fx is equal to fy, right? So we know I can operate f on both sides. So I can rewrite this as fx of f is equal to fy of f for all your f belongs to n star. Now from this definition we know what is fx of f and fx of fy of f. So if you substitute that here, you will be getting f of x is equal to f of y. So we can rewrite this as f of x minus f of y is equal to 0. And since f is linear, we can write f of x minus y is equal to 0. This is because f is linear, right? And we know f of x is nothing but norm x. So this whole thing, that is f of x minus y, can be rewritten as norm x minus y is equal to 0, right? So norm x minus y is equal to 0 implies you that x is equal to y. So in the beginning we have considered phi of x is equal to phi of y, and here we are concluding that x is equal to y. From this we can say that phi is 1 1. So now let's prove that linear mapping conditions, that is vector addition as well as scalar multiplication. So in order to prove vector addition, I can consider phi of x plus y as fx plus y. So fx plus y of f can be rewritten as f of x plus y. Since f is linear, this can be rewritten as f of x plus f of y. And we know that f of x is nothing but fx of f, and f of y is nothing but fy of f. Right? I can write in this way. So this is nothing but fx plus y is equal to fx plus fy. So again, what is fx plus y? It is phi of x plus y, and fx is phi of x, fy is phi of y. From this we can say that phi preserves vector addition. Similarly, we have to prove for the condition scalar multiplication, right? For that I will consider phi of alpha x will be equal to f alpha x. So if you operate f, it will be f alpha x of f can be rewritten as f into alpha x. Since f is linear, this is nothing but alpha into f of x. Alpha into what is f of x? F of x is nothing but fx of f. So we can write this as f alpha x is equal to alpha into fx, and fx is nothing but phi of x. F alpha x is nothing but phi of alpha x. So phi of alpha x is equal to alpha into phi of x, means phi preserves scalar multiplication. So from these two conditions I can conclude that phi is a linear. Phi is linear. So now we have to prove one more condition in order to say it is isometric isomorphism, that is norm phi of x is equal to norm x. In order to prove this, I will consider two cases. One is norm x is less than or equal to norm phi of x. Another one is norm x is greater than or equal to norm phi of x. If I prove these two inequalities, from this we can conclude that norm phi of x is equal to norm x. Okay. So now first let us consider norm phi of x. I can write norm phi of x as norm fx. Right? Since f is bounded, since fx is bounded, we can write this as this is less than or equal to norm x, because fx is bounded. Right? So from this, norm phi of x will be less than or equal to norm x. This is my first inequality. Similarly, I have to prove one more inequality. For that, I will use the consequence of your Hahn-Banach theorem. So if n is a normed linear space and x belongs to n, and your x is not equal to 0, then there exists a functional f that belongs to n star such that norm x is equal to f of x and norm f is equal to 1. This is from the consequence of your Hahn-Banach theorem. So using this we can write f of x is equal to norm x. So obviously your norm x will be less than or equal to mod f of x. Right? So norm x will be less than or equal to, now I will define my mod f of x as supremum of mod f of x such that f belongs to n star and norm f is less than or equal to 1. Okay, so norm x will be less than or equal to norm fx, because we know that f of x is nothing but fx, right? So from that I can write this whole thing will be less than or equal to norm fx. So again we know what is fx. Fx is nothing but phi of x. So from that norm x is less than or equal to norm phi of x. We can write this as norm phi of x is greater than or equal to norm x. I will call this as inequality number 2. So from inequality 1 and 2 we can conclude that norm x is equal to norm phi of x for all your x belongs to n. So phi is 1 1, phi is linear and norm x is equal to norm phi of x. Therefore we can say that phi is isomorphism. So this is how we prove this theorem. The mapping they have given in this theorem, that is phi from n to n double star. This is called as natural embedding of n in n double star. Okay, so the isometric isomorphism of this mapping, that is the isometric isomorphism phi from n to n double star, and it is defined by phi of x is equal to fx for all x belongs to n. This is called natural embedding of n in n double star. So in order to define natural embedding, we will consider isometric isomorphism mapping. Okay. So similarly, a normed linear space is said to be reflexive if n is equal to n double star. If this second conjugate space is equal to a normed linear space itself, then you can call that normed linear space as reflexive. Okay, I repeat. So if the second conjugate space n double star is equal to n, then this normed linear space is called as reflexive. The next important definition is graph of mapping. So we can define the definition, we can define graph of mapping by considering two non-empty sets, say x and y. This x and y are two non-empty sets. Since it is a mapping, I will define a mapping f from x to y, where x is domain and y is range. Then the graph of f is defined as x cross y, and this x cross y consists of all ordered pairs, and that ordered pairs will be in the form of x comma f of x. This is how we define graph of mapping. I repeat. So in order to define graph of mapping, I have to consider a mapping and set. Okay, so we are considering two non-empty sets, say x and y, and the mapping is f from x to y. Now I have to say that this mapping f is a graph. So in order to say that the graph of f is mapping, this can be defined in the form of x cross y. Okay, this x cross y, we know that x cross y consists of ordered pairs of points. So that ordered pairs will be in the form of x comma f of x. If any ordered pair is in the form of x comma f of x, then you can say that it is a graph of mapping f from x to y. Okay, this is how we define our graph of mapping. So similarly, we have one more definition, that is closed linear transformation. Closed linear transformation is nothing but, first I will consider n and n prime. This n and n prime are normed linear spaces. Okay, and let us consider a subspace D of n. We are considering two normed linear spaces, say n and n prime, and D is a subspace of n. Then a linear transformation T from D to n prime is said to be closed if and only if I choose an element xn belongs to D and xn converges to x and T of xn converges to y, implies x belongs to D and y is equal to T of x. I repeat this definition once again, just go through it. We are considering two normed linear spaces, n and n prime are normed linear spaces, and we have a subspace, say D. This is subspace of n. Then a linear transformation T from D to n prime is said to be closed. This mapping is said to be closed if xn converges to x, where your xn belongs to D, and T of xn converges to y, implies x belongs to D and y is equal to T of x. That means the converging point should also belongs to the subspace D and y is equal to T of x. If this condition is true, then you can say that any linear map holds this condition, then that linear mapping is said to be closed linear transformation. Now using these two definitions, let us prove one important theorem. The theorem name is the closed graph theorem. Okay, so the statement of the theorem says that let B and B prime be Banach spaces and let T be a linear transformation of B into B prime. Then T is a continuous mapping if and only if its graph is closed. So we have two Banach spaces, say B and B prime, or you can just say that n and n prime are normed linear spaces. Okay, since it is Banach space, it is also a normed linear space, right? I can say that B and B prime as normed linear space as well as a Banach space. So B and B prime are two Banach spaces and the transformation is from B into B prime. That means we can define T from B to B prime, where B and B prime are Banach spaces. Okay, the next part says that then we have to prove that this T is continuous mapping if and only if its graph, that means I will consider that mapping as TG. Its graph means T suffix G. Okay, this is closed. We have two parts to prove here. One is direct part. In the direct part, I will consider T is continuous and I will prove that TG is closed. In the reverse part, that is conversely, I have to prove that if TG is closed, then T is continuous. Okay, so let's prove the direct part first. First, we have to assume that T is continuous, right? Before that, from the given statement, we have B and B prime are Banach spaces. And they have given one more thing, that is T from B to B prime is a linear map, right? So then the graph T is closed. They have given that graph T is closed. Sorry, they have not given that the graph T is closed. We have to prove. Before proving that part, let us consider how the elements will be in graph T. Okay, so the graph T will be denoted as TG. So from the definition of closed linear transformation and graph of mapping, I can write that TG is a graph and it will be in the form of x comma T of x. We have seen in the definition of graph of mapping, we have x and y as a non-empty sets and x is a domain x, y is a range in y. So f from x to y is a mapping. If I want to say the graph of f, if I want to define the graph of f, it is a x cross y, right? And it will be in the form of ordered pairs, and ordered pairs can take the form x comma f of x. Here the mapping is f, so x comma f of x. In this statement the mapping is t, so it will be in the form of x comma t of x, right? Such that your x belongs to B. So I can write this is a subset of B cross B prime, Cartesian product of B and B prime. This is again from the definition of graph of mapping. Now, in order to prove TG is closed, we know that from the knowledge of topology, we have seen that if I want to say A is closed, then the condition holds is A can be closed if A is equal to A closure, right? So similarly, if I want to say TG is closed, I have to prove that TG is equal to TG closure. I am just using the concept of your topology in order to prove that TG is closed. So any set can be closed if its closure and the set is equal, right? So TG is equal to TG closure implies you that TG is closed. So now in order to prove TG is closed, the data they have given is T is continuous, right? So now I will consider 2 points, say x comma y, and it is belongs to TG closure. If I prove x comma y belongs to TG, then I can say that TG is closed, right? Before that, in order to prove TG is equal to TG closure, I will use 2 cases. One is TG closure is subset of TG. Another one is TG is subset of TG closure. If these 2 conditions are true, then I can say that TG is equal to TG closure, right? So for that, we have considered x comma y belongs to TG closure. So we know that A closure is nothing but A union derived set of A, right? Or what is derived set? That is also you have already studied in your previous semesters, right? So the set of all limit points is nothing but your derived sets. This is how you define your derived sets. So limit point is nothing but every neighborhood of x contains a point of A other than x, then that is nothing but limit point. Set of all limit points is called as derived sets. So now I can define A closure as A union derived sets of A. So similarly for this, if x belongs to y belongs to TG closure, means this TG closure will be equal to TG union derived sets of TG. So this implies that x comma y belongs to TG or x comma y belongs to derived set of TG. From this I can say that you can choose any of these two, which says you that x comma y is a limit point of TG, right? So if x comma y is a limit point of TG, then there exists a sequence, and that sequence will be in the form of xn comma t of xn that belongs to TG, such that I can write that as limit n tends to infinity xn comma t of xn is equal to x comma y. I will call this as equation number 1. So this is from the definition of your closure. So you can write A closure as A union derived set of A. So using this concept, I can write x comma y belongs to TG or x comma y belongs to D of TG. D of TG is nothing but derived set of TG. So from these two we can conclude that x comma y is a limit point of TG. So if it is a limit point of TG, then obviously there exists a sequence. Sequence is not here, the sequence we considered is xn comma t of xn, and this sequence converges to TG, belongs to TG. So we can write this in the form of limit n tends to infinity xn comma t of xn is equal to x comma y. That means limit n tends to infinity xn is equal to x, and limit n tends to infinity t of xn is equal to y. I will call this as equation number 2 and this as equation number 3. So in the statement they have already given that t is continuous, right? So t is continuous means we can write this as limit n tends to infinity t of xn is equal to t of x, right? So what is limit n tends to infinity t of xn? It is nothing but y. So y is equal to t of x. This is by equality 3. Now I can write x comma y is equal to x comma t of x, and this is belonging to TG. Initially we have considered x comma y belongs to TG closure, and now we proved that x comma y belongs to TG, right? So therefore I can say that TG closure is a subset of TG, but TG is always a subset of TG closure, because A closure is nothing but A union derived set of A. From this I can say that TG is always contained in TG closure. So now we have these two cases, we can conclude that Tg is equal to Tg closure. This is the direct part of the proof. Next, I have to prove the converse part. That is, I should consider Tg is closed. Using that, I have to prove that T is continuous. Right? So now the data is Tg is closed. We have to prove that T is continuous. So now they have given two Banach spaces, that is B and B prime. If these two are Banach spaces means this implies that B and B prime are complete spaces. Right? Because from the definition of Banach spaces, any space which is normed, linear and complete, then you call that as a Banach space. So if B and B prime are Banach space means B and B prime are complete spaces. So if these two are complete spaces, then Cartesian product of B and B prime is also complete. Right? Now from this, if you consider any closed subspace of a complete space, then that is also complete. That means closed subspace of a complete space is also complete. This is a known thing, right? So now that means Tg is complete space. Because from the data we know that Tg is closed, so using that I can say Tg is also complete. Now let's define a mapping F from Tg to B such that f of x comma t of x is equal to x. So if you observe this, you can directly say that f is 1 1 onto and a linear map. Right? Therefore, I will directly consider that norm of f of x comma t of x is equal to norm x, and obviously this norm x will be less than or equal to norm x plus norm t of x. That is nothing but norm f of x comma t of x will be less than or equal to norm x comma t of x, right? I can write this as 1 into norm x comma t of x. We can write this because we know that norm of x comma y, if I consider a product topology of n and n prime or b and b prime, we can write norm x comma y is equal to norm xp plus norm yp whole power 1 by p. Okay. If p is equal to 1 here, this will become norm x comma y is equal to norm x plus norm y. In our case, we have norm f of x comma t of x. So this will be less than or equal to norm x comma t of x. So if you write, this is because you can observe here, for this we are substituting this, right? So if norm f of x comma t of x is less than or equal to norm x plus norm t of x, you can write this in this form. Here in the place of norm x and t of x, we have f of x and t of x. So from this we can write that norm x comma t of x. Just check the position of the elements, you will understand. So from this you can say that f is bounded, right? F is bounded. So boundedness implies continuity, so f is continuous. Now we have f from Tg to B prime is 1 1 onto and continuous. Also we have Tg and B prime or Banach spaces. This implies F is homeomorphism, right? Now, if F is homeomorphism, then there exists F inverse, because the known fact we have is a one-to-one continuous linear map of a Banach space B prime or B. I will write it here. So a one-to-one continuous linear map of B and B prime is homeomorphism. That means in particular we can say that if a one-one linear map T of a Banach space B onto itself is continuous, then there exists inverse. I can say that as T inverse. This is automatically continuous. This is well-known fact. So using this fact, I can say that F inverse is also continuous. So we can define our mapping F inverse as B to Tg, and this is continuous. If this is continuous, I can say that it is bounded. That means I can write norm T of x is less than or equal to norm T of x plus norm x. So this is nothing but norm x comma T of x. So norm x comma T of x is nothing but, from this mapping, this is nothing but norm F inverse of x. That is norm T of x is less than or equal to norm F inverse into norm x, right? So from this you can say that F inverse is bounded, and so T is bounded, right? T is bounded means T is continuous. So we used the fact that Tg is closed. Using that I have proved that T is continuous. You should remember this part very clearly. So till here F is homeomorphism, till here there is no doubt, I guess. So from the known fact we will consider that F inverse is also continuous. So you are just defining a mapping of F inverse, and from that I can write norm T of x is less than or equal to norm T of x plus norm x. This is nothing but norm x comma T of x from the definition of product topology. So from the defined mapping, this is nothing but F inverse of x. So if this is equal to norm F inverse of x, then obviously your norm T of x will be less than or equal to norm F inverse into norm x. From this, if F inverse is bounded, so you can say that T is also bounded. Boundedness implies continuity. So you can conclude that T is continuous. This is all about closed graph theorem. In the next session, let's prove open mapping theorem as well. Open mapping theorem. For that we need one supporting lemma. First I will prove that lemma in the next session. Then we will continue with open mapping theorem. Thank you.